All right, in this video I'm going to try to wrap up section 4.9. We're talking about antiderivatives. And an antiderivative of a function is another function whose derivative is the function that was originally given to you. Okay, and so we've looked at some examples of finding antiderivatives there on the previous page. And of course we have to know derivatives. Derivatives do not go away completely, but this is a new topic that we are introducing here. The rest of the semester is going to be all about antiderivatives. Okay, so this is a this is an essential thing that we're looking at here that's going to carry on really for the next several chapters in the book. Okay, we'll talk more about that as we go along here. But let's take a look at some more examples. Here's one. We want to find f of t if f prime of t is 4 divided by the square root of 1 minus t squared, and f of 1/2 equal 1. Okay, so let's first find the general antiderivative. 4 is a constant, so I can leave that alone. Constants can come out of antiderivatives just as constants can come out of derivatives. And so I need to think of a function whose derivative is 1 over the square root of 1 minus t squared. The derivative of sine inverse of t is 1 over the square root of 1 minus t squared. Okay, and then I'd want a plus c there at the end. Now, f of 1/2 is 1. So if I were to plug 1/2 into this function that I've created here for t, then I'm looking at 4 times sine inverse of 1/2 plus c. Sine inverse of 1/2 would be pi over 6, since sine of pi over 6 would give you 1/2. Multiply by 4, that gives you 2/3 pi when you reduce, and then plus c. Okay, now f of 1/2 is 1. So when I set 2 pi over 3 plus c equal to 1, then c would be 1 minus 2 pi over 3. That would be the exact number, and you keep it in an exact form here. So my particular antiderivative would be f of t equals 4 times sine inverse of t plus the constant, which is 1 minus 2/3 pi. Okay, here's another one. Find f of x if f double prime of x is 3 divided by root x, f of 4 is 20, and f prime of 4 is 7. Okay, well, let's start with f double prime of x. That's the same as 3 times x to the negative 1/2, which is how I'd want to think of this because I'd want to begin by using the reverse power rule. Okay, you're going to add 1 to the power and then divide by the new power. The 3 is a constant. Constants can come out of antiderivatives. So f prime of x would be 3 times x to the 1/2 power divided by 1/2. That's the same as multiplying by 2. And then plus a constant. I'm going to call this constant C1 just because there's going to be another constant that I'll be getting when I find f of x. Now, f prime of 4 is 7. So here's f prime of x, what I've got so far. Let me plug in 4, and I'm going to have 6 times the square root of 4 plus a constant. Square root of 4 is 2, 6 times 2 is 12, plus a constant. Okay, f prime of 4 is 7. So if you get 12 plus a constant equals 7, subtract 12 from both sides, that means that constant, which I'm calling C1 here, is negative 5. All right, f prime of x, therefore, would be 6 times the square root of x minus 5. I'm going to keep this in rational exponent form because when I find f of x, I'm going to want to use the reverse power rule on this guy again. 6 can be left alone, and so the antiderivative of x to the 1/2, that'd be x to the 3/2 divided by 3/2. If you're dividing by 3/2, that's the same as multiplying by 2/3. Minus the antiderivative of 5 would be 5x. And then plus a constant. 12 over 3 is 4, x to the 3 halves minus 5x plus a constant. Okay, now they told us that f of 4 is 20, so if I plug 4 into this function here, 4 to the 3 halves power, well 4 to the 1 half is 2, 2 cubed is 8, times 4 is 32. Minus 5 times 4 is 20, and then plus a constant. Okay, we get 12 plus a constant. Now f of 4 is 20, so if you have 12 plus a constant equal 20, that means that the constant would be 8. All right, f of x, my answer, would be 4 times x to the 3 halves minus 5x plus 8. If I were to calculate f double prime of x, I should get this right here. And of course, I could check that. The nice thing about antiderivatives is that you will always know if you have the right answer. Take a derivative and see if you get back to what you started off with there. Now, I'm not going to make you guys check your answers, but it's a good idea to, if you're ever unsure, take a derivative, okay? And, you would know if you get the right answer or not. Here's another example. Let's find s of t if v of t is 2t minus the quantity 1 plus t squared to the negative 1 power. S of 0 is 1. Okay, s is a position function of an object at time t. V is the velocity function. Well, the velocity function is the derivative of the position function, right? So here's s prime of t. That's 2t minus, I'm going to write this as 1 over 1 plus t squared. I need to know the antiderivative. Well, antiderivative of 2t, you're going to add 1 to the power, divide by the new power. That'd be 2t squared over 2. The 2's are going to cancel there. And then minus the antiderivative of 1 over 1 plus t squared, that is tangent inverse of t. Plus a constant. The 2's cancel there, like I said. And so here's s of t. Now s of 0 is 1. So if I plug in 0, 0 squared is 0, minus tangent inverse of 0 is 0, because tangent of 0 is 0, plus a constant. Okay, so s of 0 equals 1 is essentially them telling me that the constant is 1. So the particular antiderivative then would be s of t equals t squared minus tangent inverse of t plus 1. That'd be the answer. Here's some notation for antiderivatives. We're going to look at this in Chapter 5. They don't introduce the notation quite yet, but there's no problem with talking about it now. We're going to be using it all over the place, starting in Chapter 5 and really for the rest of the entire book. Okay, you'll be using what's called integral notation for Calc, the rest of Calc 1, Calc 2, and Calc 3. Okay, let's let capital F prime of x be equal to little f of x for all x. Okay, so capital F of x is an antiderivative of capital F prime of x. Now, the notation that we're talking about here for antiderivatives is called integral notation. This is the integral sign. F of x, the function, is called the integrand, and then dx is called the variable of integration. Now in this notation, you are just simply describing to somebody that you're going to calculate the antiderivative of little f of x. Well, that would be capital F of x plus a constant, right? That's where it would be the general antiderivative. So let's take a look at some examples. Suppose that I wanted to find the antiderivative of 3x squared minus 7, or the integral for 3x squared minus 7, we would say. Well, I can use the reverse power rule on the first term, right? You're going to have 3 times x cubed over 3, the 3's are going to cancel, and then minus the antiderivative of 7 would be a 7x. Plus constant, this is the general antiderivative, right? And so my answer then would be x cubed minus 7x plus a constant. Okay. One note here, when you're using integral notation, which we will be doing all over the place for the rest of the course, make sure that you include the variable of integration. Okay, if you don't have dx or dt or dy or whatever it is, I'm taking points off because that's bad notation. We'll talk about that more as we go along, okay? But just like everything else that we've been doing for the semester, the notation matters. You don't want to slip up on that. Make sure that you're writing the integral sign as well. Once you've calculated the antiderivative, don't be writing the integral sign anymore. Don't be writing dx anymore, okay? And also, as I've mentioned several times, make sure that you got the plus c there at the end. Here's another example. Suppose that we want to find the antiderivative of 2 minus sine t. Well, here's how we'd write that using integral notation. Dt is the variable of integration, okay? And so the antiderivative of 2 would be 2t minus the antiderivative of sine t would be negative cosine t, since the derivative of negative cosine t would be sine t plus a constant. Okay. 2t plus cosine t plus a constant then would be my answer. By the way, if somebody were to write dx here, then 2 minus sine t would be thought of as a constant. And this would not be the correct answer then. It would be 2 minus sine t times x plus a constant. It would be a totally different problem. Okay, so make sure that you don't blindly write dx all over the place if the variable is not x. You know, if the variable is t or y or whatever, you know, make sure that you got the correct variable of integration there. Here's one more. Suppose that we want to find the integral for 3y to the power root 2 minus 1 minus y to the power 1.7, and we're integrating with respect to y. Okay, WRT means with respect to whatever, you know. Well, this is the same question as asking for us to find the antiderivative of the integrand. Okay, that's the expression inside the integral here. 3 is a constant, we'll leave that as is, and we'll apply the reverse power rule then. You're going to add 1 to the power, divide by the new power. So if I add 1 to the power here, I'm going to have root 2 and then divide by the new power, minus y to the power, you're going to add 1 to the power, that's 2.7, divided by the new power, 2.7, plus a constant. Okay, and that'd be my answer. That would be the antiderivative there. Be sure that you look over the homework problems in this section. Okay, as I mentioned earlier, we're going to be talking about antiderivatives to finish out the rest of Calc 1, and so much of what you do in Calc 2 is all about antiderivatives and integrals. Okay, probably 90% of that course is all about integration. So you see what's happening here next is, like, we're going to talk about the rules for antiderivatives, and we'll get some practice calculating antiderivatives, just like we did with derivatives. You know, we'll get some practice calculating, and then we'll turn our attention to applications. Okay, in Chapter 6 we'll look at some applications, and then Chapter 6 is where we're going to end Calc 1, but in Calc 2 you'll pick up with more application problems, and you'll also talk a lot about integration and more in that class. Okay, and I'll kind of mix in some things with Calc 2 as we get to the next chapter, and so anyway, the homework is on page 355, and yeah, be sure to look at the odd numbered problems there. We're now done with Chapter 4.